All right. Good afternoon to everybody who's online, and good afternoon to our guests that are visiting us in person. This is the second of our free seminars that we are going to be running once per month. 180 Materials Engineering Solutions is a company based in Cape Town, South Africa, and we specialize in materials engineering consulting as well as accredited materials testing. And today our seminar is on the challenges of testing of composite materials for marine vessels, specifically for class for the classification societies such as Bureau Veritas Marine and Offshore and various other accreditations. And so without further ado, I'm going to introduce you to Sarah Virgin, who's going to be giving the presentation today. Thank you very much.
Hello, I'm Sarah. For those of you online, and thank you for everyone coming in. Today I'm going to talk about composites in the marine industry. I'll also be focusing on just giving information as to a bit of background on them, but also tying into how materials testing and mechanical testing can be used for quality control of composites and how that can help improve the quality assurance of the marine industry and boat building. Okay, so just an overview of the presentation. I'm just going to give a brief discussion of composites. What are they? What are the most common variants of composites, and particularly those that we see in the marine industry? And then I will do a comparative discussion on composite properties versus metal properties, and when composites would actually be the preferable material to metals in terms of boat building or use in the marine industry. And then we'll talk about the verification of quality control by way of material and mechanical testing. So what I alluded to in the beginning. And then also how compliance can help with quality assurance of composites. So let's first start with composites as an engineering material. You get three typical composites or common composites in the marine industry, and those are carbon fiber laminates, glass fiber laminates, and also sandwich composites. So carbon fiber laminates are extremely strong. They're also very lightweight, and that's why they are being used quite extensively, not only in the marine industry, but also in automotive, aeronautical industries too. They are often manufactured in a directional layup. So you'll see the picture on the left. They'll be set up in a specific direction depending on the application of the composite. And also depending on the application, you're able to, with all composites actually, manufacture to a specific thickness or dimension that you'd like to achieve with your build. So glass fiber laminates can also be built in a directional manner. So they can be built in with glass fibers in one direction or in two overlapping directions. And that's typically what you'll see in the boat building industry, because it is the most versatile in terms of load distribution through the composite, but we'll talk a bit more about that. You can also get chop strand, which is where there is no specific direction of the fibers within the composite, but that's not typically used in a structural application. In a structural application, you do want to understand which direction your fibers are laid down in, because that's where your strength and where your maximum material property you'll get, or the most you'll get out of them. Sandwich composites are quite interesting, and they're often used in the manufacturing of boat hulls or decks, so the structural sort of frame of a boat. And they can be built from either carbon fiber laminates or from glass fiber laminates, but their build-up, as the name implies, is a sandwich between the laminate, two laminates actually, and a foam core on the inside. So it's sandwiched between this core. Typically for vessels, we've often seen glass fiber laminates being used for sandwich composites with a PVC core. And what that helps with is PVC is quite light and you'll get quite a good buoyancy for the vessel from using that material. Okay, so in terms of how composites are manufactured or how are they used in manufacturing versus how metals are worked with, especially for in terms of boats. Metals are typically welded. They are taken from plates, as can be seen below, and any sort of fittings. In the top there, you can see a window fitting being manufactured or welded, actually. So it's very strong, yes, but it is labor intensive and it does pose a high risk because if the weld is not done correctly, if the procedure isn't qualified, you're at risk of failure. Whereas composites, you are able to actually build an entire vessel in one go if you have the correct mold. So you'll use a wooden frame and design a mold of the vessel that you'd like to make if it's a yacht or a larger vessel. And that mold will be set up so that you can lay down, in this case, it's glass fiber laminates. So you lay down the laminates in the shape that you'd like, and then pour resin over it and cure it in one go. So in that way, you're also able to monitor it quite quickly. Monitor it well, but also once the mold is set up, that is your most labor intensive part of manufacturing a composite hull is the mold. If it's set up properly, you can manufacture multiple composite vessels from one mold, and the curing time is far quicker than what it would take to construct a typical vessel from steel or aluminium. And also, yeah, you can use composites everywhere in the ship. So you can use it for hulls, cabins, decking, um, bulkheads, ceilings. You can also use it for repairs, and it does pose an advantage for repairs because if in a metal structure, like the one on the bottom left, there's welded components, there's I-beams, you'd have to remove an entire section because of the structural integrity of the boat to conduct a proper repair. Whereas with composites, you could be able to isolate the specific area and only repair that small area if it was impacted or something happened to just that area. You don't have to remove an entire section of the boat. Okay. Now, composite properties, metal properties, what's the difference? Why would one be better than the other? In terms of density, composites are extremely lightweight. And if you're using them in a marine vessel, that lightweight aspect can actually cause you to create a vessel that's much more fuel efficient, which means nowadays you're impacting on a smaller carbon footprint than what a larger vessel needing more fuel would use. Carbon fiber typically has a density between 1,600 and 2,000 kilogram per meters cubed. Glass fiber is also similar. Like I said, the foam cores, such as PVC, can have a density of 100 kilograms per meters cube, which is extremely light, which also helps with the design of the vessel. The lighter your vessel is, the more you can actually put onto the vessel in terms of storage, equipment, and also just get a much more efficient use out of the vessel. So metals, on the other hand, just as a comparison, aluminium has a density of 2,700 kilograms per meters cubed, while structural steel is far higher at 7,500 to 8,000 kilograms per meters cubed. So compared to composites, metals are much more dense, which means that the more you use, especially as you get larger with a ship, it will be a much heavier ship, and you have to make sure that you're meeting your buoyancy requirements through calculations. And also you might not have as much flexibility with storage, what can go onto the vessel or not. So flexural bend properties with metals this property, yeah, it's more required for manufacturing. So when you manufacture, say, the side of a vessel, you're going to take a plate and specifically shape it into that form, and that's a way of bending it. But it's also used particularly for weld defects. So during a weld procedure qualification, a bend test will be conducted to see, are there any voids in the weld, are there any cracks in fusion line, and it's basically just a go no go test to see if the weld will survive any sort of catastrophic failure or not. So just as an example, there you can see an example of a weld that has no voids in after a bend test, so it's appropriate. And then also an example of one where there is cracking and there is voids within the weld, which might not be structurally sound to use on a vessel. Whereas composites, you're not required to bend it during manufacturing, so it's not as important to understand the bend properties of the composite, but rather the flexural properties of it. So composites, because you're molding it, you're able to get a much more complex, sometimes more complex actually, the shape or design of a hull, and rather than shaping it from a metal. But what a flexural test does, or bend properties of composites can help understand, is when delamination will occur. And that is a catastrophic failure in terms of composites. And it's important for a designer or manufacturer to understand when that would happen. For sandwich composites, it's also helpful to know when the adhesion between the laminate and the foam core will separate. So if by any chance you can estimate the risk of the composite experiencing a flexural load during operation, if it bumps against something, or that you'll be able to know how much play you'll be able to have on it, and also in the design of a vessel. Impact properties are an important property for metals specifically. Usually a Sharpie V-notch test is conducted to determine the ductility of the material. Yeah, it's a quick check for material toughness. Yeah, because you want to understand whether the material itself will be ductile when it fails, or whether it'll be brittle. And as a designer, you don't want the material to be brittle, because that can result in catastrophic failures. If it's ductile, hopefully if there is an impact, it won't puncture the actual vessel, but rather it will make an indent, and the vessel will be able to get to shore safely before actually taking on water. The impact test is also specifically important for S355JR or S355J2, those types of materials, because those materials are manufactured for a specific use in specific temperature waters. So JR material is specifically meant for use at room temperature, while J2 material can be used at minus 20 degrees Celsius. So it can be used for vessels that are intending to sail in Arctic seas, or that, whereas JR would not be suitable for that application. Yeah, metals are not meant for drop impacts, while composites are. Composites, you don't really do Sharpie V-notch or IZOD impacts, because you're not trying to see ductility or brittleness. It doesn't have that property. Typically, sandwich composites are tested for impacts, just to see whether, or at what impact energy that sandwich composite will be punctured. So that would be in the case of a sharp impact, if something in the water accidentally pierces the vessel, or you sail into something. But another reason why so metals actually would be better for use in colder climates, so like the Arctic, than composites, is because composites are made from different materials. They have different thermal coefficients, so they could potentially crack due to the thermal changes. So they're not as suited for icy waters. But when I say icy waters, I'm talking about like going closer to Antarctica or the Arctic. So tensile properties. So Metals, tensile properties for composites as well, they're exactly the same. It's the same type of test, just different shape material, which we'll go into or sample. Um, but you're able to determine from both for metals and for composites the different failure modes of the material. For metals, the tensile test is typically done for welder joints, especially in the marine industry, to see if the weld is strong enough for its application. The typical ultimate tensile strength of S355JR is between 450 to 680 megapascals, while that of aluminium 6061, which is a standard structural aluminium, is 290 megapascals. These are just examples of tensile tests for metals. Another way, or just to emphasize the failure modes of metals, is you'll also be able to tell whether it's a ductile or brittle material from its tensile test. For composites, you still want to understand the failure mode of the composite, but how it fails will be different to that of metals. So as during design, you want to know whether it will delaminate, whether it'll split, whether it will break laterally, if it will explode. And also you want to be sure that you're testing in both directions, because a composite might not be homogeneous. So you might, and that comes back to how the composite is laid up. Is it laid up in the exact same, with the same fibers in the longitudinal direction and the transverse direction? Or is there a difference between the longitudinal and transverse direction? If so, you'd have to test for the tensile properties in both directions, because they could be different, and that could govern when your composite will fail. The ultimate tensile strength of carbon fiber is approximately 900 megapascals, which is actually better than aluminium. So just as a comparison, and that of glass fiber is 180 megapascals, which is on par with aluminium. So it's actually, from a strength point of view, very similar to metals. Obviously, steel is still stronger, but for the purpose of smaller vessels and that, I mean, if you're going to be using aluminium or intend to use aluminium, you could potentially use a composite instead, and it'll have the benefits of being lighter and easier to manufacture with. This is just examples of different ways that the composites can fail, and this is governed by, depending on the standard that you are testing against, they'll show different acceptability limits. But for example, and they'll have codes, so you'll know exactly where the composite fails during the test, and also how it fails. Yeah. So now that you understand the properties, it ties very well into the actual test that you can do and why you would do certain tests. So density, first of all, you can test for the mass per volume of the sample. It's very quick, but it's done for quality control to check for voids in the material. So during manufacturing, was the resin completely devoid of air particles or air molecules during the curing process? You're also checking that if the correct materials were used during the manufacturing process, and that ties into compliance as well, because when you're audited, they will make sure that the materials you listed, the expected density, that you are meeting that after manufacturing. And like I said earlier, is important for fuel efficiency calculations, but also FEA simulations. Once the model has been designed, it's often put into finite elements analysis or computational fluid dynamic analysis. And in order to accurately get proper results from those simulations, you'd have to have the correct material properties, and density ties into one of those properties that are used in those simulations. So reinforcement content by weight is a test that complements the density tests. It's done for a similar purpose. The test determines the percentage of fibers that are within the laminate skin. So it consists of burning off the resin in the laminate until you are left with only the fibers. From a quality control perspective, if you have set out that my composite laminate should have 4 layers of this many fibers, you'll be able to confirm that with the reinforcement content by weight that you had used the correct amount of fibers for the composites. So yeah, you're just checking the design specifications from the designer. Yeah. Like I said, the 3-point bend test is typically used, but for flexural testing in general, you're trying to, on a composite, determine deflection before failure, because once again, it can help your design models. A designer or neighbor architect can understand how much play they have within their design. Do they need to reinforce a specific area, or are they able to push support slightly further away? They'll be able to know. Once again, you also want to determine what the failure mode is under flexural force, because interlaminate shear is strictly prohibited. Interlaminate shear would be when the um, cracking occurs in the composite but parallel to the fibers. And the reason why that is so detrimental is because there is no resistance to that crack forming if it starts in a parallel position. So once that crack forms, it will continue if it's not detected. So you could end up with an entire, I actually have done a case where the whole deck was delaminated and it's lost all the structural integrity just from a delamination crack. In terms of sandwich composites, again, you want to check the adhesion of the foam core to the laminate skin to understand at what force that adhesion will fail. Yes, so this is also just a visual to help understand. So tensile fractures on the outside, that's fine. Yeah, tensile fractures of the fiber, tensile fractures of the outermost layer, compressive fracture, those are all acceptable failures of a composite. But as soon as there's interlaminate shear involved, the risk is that that crack cannot be stopped. So that is why it's not accepted. And this is again from a standard, so it'll guide you as to what to look for during your quality control process and testing process. So impact testing, like I said, you can do drop impacts to simulate small high velocity impacts. I think some companies have actually started investigating using composite cladding for bullet holes in high risk areas. So that's quite interesting. We did a test a while ago as a case study. So Sky Advance, they were preparing sandwich composites also to manufacture vessel hulls. And they wanted to, as a comparative analysis, see how aluminium that would be also used for a vessel hull of that size would fare against those sharp impacts, the drop impacts. And it actually, at some impact velocities, the sandwich composite fared better than the aluminium. The aluminium was punctured directly through, whereas the sandwich composite, that first composite layer, laminate, was affected, but because the PVC foam behind absorbed that energy, it didn't puncture all the way through to the last or to the back laminate, which means that you wouldn't have had water penetration into the vessel. You would have had into the foam, but not into the vessel. Whereas with aluminium, you would have had water going straight in through there, which was very interesting case study. For tensile testing, again, I'll go through this quickly, but yeah, you want to know if it's isotropic, or because you want to know whether you have to test both in the longitudinal or transverse direction to understand the difference in their ultimate tensile strength and tensile behaviors in the different directions. It's important to understand the tensile properties. You can get a lot of information from just one test, but those properties are most useful for the design, sometimes even purchasing, understanding what kind of strength you require, and also maintenance, to know how well your design will last. So tensile properties are also crucial, like density, to any computational fluid dynamic or finite elements analysis simulations during the design process. So you can theoretically, as a naval architect, work out and you will design the type of composites that's required for the vessel, and that will include the estimates a tensile strength that the material will have. But once you test it, you need to test it to ensure that you are getting your theoretical specifications. If not, if it's higher, obviously that's much greater, and you can, be happy that your design is sufficient. If it's lower, you can still put it into these simulations to see, okay, the tensile strength is not where I thought it was. Would the vessel still be able to survive the loads and conditions that it will experience at sea? So you'll be able to, before either selling the product or putting it out onto the ocean or wherever, you'll be able to tell whether the um, vessel will be fit for purpose or not. Yeah, so that's just also visual to show how a composite could differ in directionality of the fibers, and that might affect the tensile properties. But once again, it's exactly the same as a metal. You still look at stress, you still look at the strain that the material um, experiences. It just doesn't have a very long plastic deformation. So once it starts yielding, very soon after yielding, it will fail. As another case study, we did some work a while back for Evolution Marine. They wanted to do a quality control test on their deck plate that had appeared to cure unevenly overnight while they were manufacturing a 60-foot hull. Um, and what we did just to do a quick check for them was a tensile test. So through our testing, we found that the ultimate tensile strength of the internal skin was 111 megapascals, while the external skin was 64 megapascals. So there's a complete difference and a significant difference in tensile strength of the two materials that are supposed to be exactly the same. They thought perhaps it might not have cured properly, so they tried a second cure. And after that, there was still a difference between the two. As you can see, it was 156 megapascals for the internal skin and 99 megapascals for the external skin. So the outcome is that the center of the sandwich composite deck was below their expected UTS values because it cured improperly and there was an air bubble, which I'll show now. Basically the effect. They didn't realize that the valve wasn't closed during curing, but they managed to pick this up. And because of that, they were able to, unfortunately, redo the whole thing. But rather that, a few, couple of thousands of rands replacement of the deck and redoing that, compared to a failure at sea of their clients, which could cause litigation in the end. And perhaps even, loss of life. Yeah. And you can see very clearly here that's supposed to be the exact same color, but the milkiness was their indication that something had gone wrong during the curing process. So it was a visual cue that alerted them to this error, but it was the tensile testing that confirmed it and verified it for them. Now, there are other tests that you can also do on composites, such as ultrasonic testing for void detection. That's often also good for maintenance down the line, just double checking things. You can also do lap shear testing for shear properties and failures. It depends on where your composite is being used. Is it going to experience a shear force? And also you can do thermal testing like differential scanning calorimetry to ensure that the curing phase was done correctly. So that's often done in the design phase of composites before they've selected the exact design of the build, or other tests than the ones I have mentioned yet. Okay, now through testing, and that part of testing is also compliance. Testing falls part of that. And compliance will help with quality assurance of your product. So part of it is ensuring material compliance. So a lot of testing is required to ensure that the material properties meet the data sheets, meet your theoretical calculations, the analytical calculations. And also if it's on the raw materials, you're holding accounts as accountable, sorry, suppliers accountable, are you getting what you actually ordered? And that's in terms of the fibers, the resin, the BVC foam adhesives. Those can all be tested for material compliance. But also you can look at design or manufacturing quality assurance. So that's where, like I said, with the tensile properties, you want to compare your test results with theoretical calculations. It can improve your CAD models, your computational fluid dynamic models, so that you actually get a better understanding of the vessel, of your design. In a way, it is similar to a weld qualification. A weld qualification, you're also trying to ensure that the weld that was procedure that was designed, that it will work in application. And that's the same thing that you're trying to do with a composite, is you're trying to make sure that as best as what you can, you've ensured that this product is going out into application, with ensuring that it should be fit for purpose. So yeah, the largest thing and what we work a lot in is failure mitigation. So by doing testing, by making sure you're complying with the applicable standards and guidelines, you can ensure that the appropriate design for the project is used from initiation. And that's where I say testing can help improve your simulations. You can get a much better idea, and that can lead to iterative design and more efficient use of materials and also of design features. But you can also identify weak areas within your build, and depending on what they are, you can decide to either replace it or reinforce it, but at least you'll know beforehand. So you can make improvements on there from the design and manufacturing process. And also you can prevent catastrophic failures, and that's where no one actually wants to experience or be involved in. And compliance is also about keeping traceability. So during the manufacturing process, where did you get the product? How did you manufacture it? How did you ensure that this vessel is safe to use? And that's often through testing and through compliance, meeting those requirements. One aspect of compliance that you could apply for, especially if you are boat builder that's you are making multiple designs, you can apply for type approval. So for repeat products, if you know you're going to be using the same materials, the same mold, like I said earlier on, the same design, you only have to qualify one vessel, go through that whole qualification process. And if you can show traceability and make sure that your documents are up to date, that each of your repeats will be using the exact same, you can manufacture without having to do those quality tests again. But because you have done proper analysis in the beginning and you have kept up the documentation, that's also important. You can't just drop it after that. Yeah. So compliance is all about reducing risks, which means you also have a better chance of ensuring warranty claims from insurers. But you have to keep traceability. Part of traceability is also testing, and classification does tie into that. So if you're classified with DB, with Lloyd's, all they require as well is documentation. Have you done your testing to ensure that what you have designed is what you have manufactured and it is how it's going to operate? You're also increasing the lifespan because you're ensuring no unnecessary failures, no unnecessary repairs because of poor structural material. You're improving the design through those better simulations, which can help with fuel efficiency, also reducing the carbon footprint of the vessel. And also you're building and ensuring your reputation through the proof of safety and compliance. And as a boat builder, if you're a company, everyone understands the importance of reputation. Once you've lost it basically, and you don't want to lose it. It's also compliance is also proof that you have built an industry standard. So the idea of good engineering practice internationally, you've shown that you're doing that. So in conclusion, I thought I would end with an analogy. Can you drive a car that is not roadworthy? And can you drive a car without a driver's license?
You can.
Yeah, you definitely can, but it can have severe consequences. So, yes, you can build without compliance, without testing. Oh, I've done it for 100 years like this, you can, but that off chance that something happens and it's not built to standard, it's not checked for the quality, if it's the wrong tensile strength that it's supposed to be, you're going to be in big trouble, basically, not only for yourself, but also for people around you. And that's what we're also trying to ensure is a safer environment for everyone else. Composites are extremely prevalent in the marine industry and they are developing as well. And that's where also testing comes into play. As technology is improving, we're also able to keep up to date with what it's capable of achieving, and also can make better recommendations from that. So material and mechanical testing can significantly improve and benefit the quality control procedure before, during, and after manufacturing with composites. If you have better documentation as well, your maintenance is going to be a lot easier. If you've put in the hard work in the beginning of the design and manufacturing process, maintenance and also, again, tying into your reputation, that will just improve going forward. By assuring quality assurance through compliance, not only will you reduce the risk of failure, but the reduce of litigation and the loss of product, but you'll also gain your reputation by putting client safety first, which will help you in the end. Yeah. Thank you very much. I don't know if anything to know. Yeah, any questions? Are there any questions from those online?
So let's unmute. Please, questions. Also, you raise your hands if there are any questions.
If you have any questions, you can raise your hand online and then we can unmute. If no questions, it's also okay.
Captain is but operational. Okay, Sarah, thank you very much for that. I thought maybe you could just expand a little bit on why porosity during curing is such a problem from a fatigue point of view, for example, and how common it is. So in my experience, people want to mix large quantities of epoxy resin to try and cure a large volume or a large area at a time instead of being patient and curing it more slowly. But then there's the risk of porosity. Maybe you could just explain why that porosity occurs and what the consequences are in terms of fatigue and what fatigue is in that particular case and delamination.
Can I use it now? Okay. Yeah, so porosity, if you pour in a whole bunch of resin into a larger area, there's not enough time for the air within that resin to actually escape because there's so much of it. So that air gets trapped and gets cured with those voids in the resin itself. But now because you have voids in between carbon fiber, if you think about it on a simplistic term, it's actually less surface area through a cross section. If you had to cut a laminate through a cross section, it would be less surface area to hold on. So your expected tensile strength, your expected adhesion is not there. From a fatigue perspective, voids are always a point of fracture initiation because there is a small stress concentration around that area, and also it is in its own way could be considered a crack because it's not supposed to be there. And that can help propagate. And also once a crack starts, if there are other voids in the area, the crack will take the path of least resistance and will follow all those voids. So you'll end up with a much more catastrophic failure than if it were just one or none at all. Yeah, I heard that.
So, as many of you know in the room, but maybe not so many online, I've just sailed 1,750 nautical miles from Cape Town to St. Helena. And the first 50 hours was in a northwesterly storm of about 40 knots and 8-meter breaking seas. And we definitely pounded through the waves for those 50 hours. And I can't imagine having a vessel with a whole lot of voids in it, because I think it would eventually delaminate even in that short space of time, in the middle of the Atlantic Ocean, where I don't think one would survive. So I think the voids are very important, and also do result in delamination, not only just the cracking. Um, I was going to ask you as well. I think what's also quite interesting about the impact tests is that the composites have the advantage of being able to absorb much more energy during the impact. But um, in addition to that, if you do have an impact, because it's quite easy to hit a container, for example, at sea, you're actually better able to put bungs into the composites to prevent the water from ingressing into the vessel, which I don't think would actually even work on an aluminium hull or a steel hull. Any thoughts on that?
I think it's more, yeah, like you said, it's better for the application. Like, and I think often, sometimes or not often, but sometimes in engineering, it's easy to think about the design alone, what's going to happen in a theoretical situation, but not its actual application. And like that, in terms of considering drop impacts, like you might not think you're going to hit something sharp or have designed it, but in case it does happen, you have prepared for that, because of the actual application of the vessel. And I mean, again, it goes on to like ensuring your as a user of the vessel or a client, your safety and your peace of mind in knowing, okay, even if I do impact something, then I can fix it up a lot easier than what a metal would. I mean, you can't, once that aluminium is pierced, there's no ways you can cover that up. You can't put a plaster over it or anything like that. So I think it is just a bit more peace of mind while you're using it.
So yeah, it's a bit more of a fail-safe type situation. So the use of composites has a lot of um, benefits as opposed to aluminium or steel. Number one, being lighter. Number two, absorbing more energy on impact. And number three, having a sort of a fail-safe type situation where you can bung up or repair the vessel and prevent it from sinking. I think also the work that you've presented um, demonstrates the intersection between insurance and engineering. So the testing that is done to show that you meet class approval or ISO approval, whatever standard it may be, we all know how quickly insurers want to sell us policies, until we want to claim. And then they're not as friendly as they were when they wanted to sell you the policy. Um, and I think that's what this testing enables the end user to have is some sort of leverage over the insurers to show that you have taken due care and you've done everything that you can to make sure that the vessel is compliant with standards and codes. What more can you do after that? If you don't do that, I think you open yourself up to a degree of criticism from the insurers or the underwriters, when it comes to claiming for a casualty. Um, and and in the case where there might be loss of life and the skipper is on the hook for manslaughter, I think it's even more important that these vessels are held up to these sort of standards. Um, I also wanted to point out that sometimes the design is created with carbon, glass, and Kevlar combinations. But then when it goes to manufacturing, and what we've seen in cases, I think before you were with us from Nigeria, where a design was approved with a combination of glass, composite, and Kevlar, when they actually went to construction, they left out the glass and the Kevlar because it was too expensive. And then the vessels would fail. So it's not just the testing at the start and verifying the design. It's also the testing as you manufacture, that you test coupons to demonstrate that each vessel is compliant with what the original design was. I don't know if you want to add anything from your experience.
Yeah, from a certification body point of view, it's too often misunderstood that when people receive or builders receive their certificates, that it's the end of of the line, and therefore they are free of any claims. It's of course still their own responsibility to do all the testing, and especially as you mentioned during the type approvals, it's their own responsibility to maintain the quality work, because we only come one time to have a look at the initial model, the prototype, and then they must ensure to control the quality, and that is done by continuous testing. And the reality is that doesn't happen. I can see it, but we can't do anything about it until something happens, and then they come back to us and say, "Well, you gave us a certificate, yeah, but it wasn't for your quality assurance." So
If I can add to that, if you look at marine maritime law in steel vessels, no work can be done to the hull and the deck without class approval. So the same must follow for a composite vessel, that if it's designed in a certain way and any changes are made to that design, it's got to go back to class approval or ISO approval to approve that change. They can't just make the change and say, well, you issued a certificate at the beginning, but you actually didn't follow what was on the certificates. So yes, so testing upfront and ongoing testing is important. Any other questions from the floor? Please, any questions? Oh, sorry, yes. Oh, while this mic is still on, let's
Yeah, sorry, I saw you're focusing, of course, on composites now, but I start reading up about HDPE and recycled plastic, and I think that's going to be like part of the future boat building. What are your thoughts about that?
Yeah, so Sarah can also comment, but in our recent publication, so we've just launched a publication called Materialer Africa et al. And we reviewed thermoplastic composites. Okay. And they're not yet commercially applied, but they have been reviewed as materials that could potentially solve the Boeing 787 crisis of delamination. So of course with cyclic loading like in yachts and airplanes, and it's a curse to be a metallurgist and fly, because you look at the wings flapping up and down and you wonder about the fatigue and the cyclic loads. Likewise, it's also really difficult to be on a yacht in the middle of the night, smashing through waves, thinking about fatigue. But these thermoplastic composites definitely will solve a lot of the delamination and fatigue problems that thermoset composites. These are thermoset composites, 2-part epoxy or 2-part polyester, certainly will solve that problem. So it'll be an interesting development in the future. But I think we're probably still about 10 years away from that. Sarah, do you want to comment a bit more?
Yeah, I think also part of it, and also I think it ties into the presentation anyways, is we want to ensure quality control and assurance. And I think until those materials have standards for them, I mean, now we have standards for composites and that does take a bit of a process like ISO or STM to set up. I mean, um standards for plastics alone and that, but maybe not necessarily for the marine space. So, but the only way to do that is through experience as well, and then feedback. I mean, a I actually had a discussion with VV regarding the one flexural test that was recommended for sandwich composites, because it wasn't actually meant for a sandwich composite, but there is no actual standard for the flexural properties of a sandwich composite. So EV, which is a classification body, they even just going to the next applicable standard, but there are issues in doing that. So the issue in our case was that the sample size was ridiculous for standard um, laboratory testing, and it didn't make sense. So I think that might be the only sort of thing. Once those new materials have got better standards, we have a better understanding of how to test them uniformly I think, across the world. Also, I'd be so interested with like thermoplastics, like the UV tolerance, like those kind of things, how they're developing that. I think it's very interesting. I mean, we're all open to new materials, but I think the only way we'll get better understanding of them is through testing and trialing it, yeah, and understanding their properties better. Take care. Yeah, that makes sense.
Okay. So if there are no questions from the online audience, we're going to just close. I think hopefully what we've put forward to you today is materials engineering is the final frontier of engineering. It's the most fast moving, fast growing field of engineering today. And we just have to look at Formula One and how Formula One has evolved over the years into the cars that we see today. And we all have our favorites team. But that's a that testament to how materials engineering has played a role in the evolution of something like Formula One. And now we're seeing materials engineering playing a role in not just performance vessels, but also supply vessels and naval vessels throughout the world. And it's thanks to the developments in materials engineering, but also we have to keep up with our standards and testing and how we test and whether the tests make sense, whether the tests actually give us the required information to mitigate risk. And on that note, I just want to remind you all of the second root cause analysis conference to be held in March of next year on the 11th and the 12th. Um, Early bird registration is open until the 30th of September. The 1st of September. So the 31st of August is your last day for early bird registration. And for more information, please go to our website, www.1-80-degrees.com/conference. Do you want to just type that into the chat, Duncan? So if you want to find out more about the RCA Africa conference, Duncan is going to put the link into the chat. And we would really love for you to participate, to put in a paper, to possibly exhibit. We're expecting a large Pan-African crowd to be joining us. So it's not going to be just a South African conference. The conference is aimed at throughout Africa. And in the marine vessel space, we have a huge lake called Lake Victoria, lots of marine vessels, many casualties have occurred. Lake Malawi, lots of water masses throughout Africa where these sort of standards and tests on these vessels and opportunities to produce vessels to end users in those areas do exist. So I think the conference is relevant to this audience, and I encourage you to have a look at the website, and hopefully you will participate in the conference. You'll also see on the website that there's an opportunity to attend a briefing session on Thursday, the 18th of September. And if you want to find out more, you can just email front desk at 180degrees.com. Jean, who you replied to participate in this presentation today. So thank you very much. So the next presentation will be given by me, and it will be focusing on 3 case studies of forensic engineering work that was used in litigation. So all of the cases have been settled. So they are in the public domain, which enables me to talk about them. And so I'm going to be presenting 3 cases where metallurgical and materials engineering has been used in litigation to fight court matters, and how the intersection between engineering and materials engineering specifically and law and insurance actually does exist. Thank you very much for being on the call today. We really appreciate your support and participation. If you want to be on a mailing list to find out about more free seminars in the future, please let Jean know. We're creating a database, and we will then send out notifications for the next free seminar, and you can stay on that database if you wish. Thank you, everybody. Goodbye.